the number is equal to. So a true positional value system, first of all, requires a base. And in our system in the United States, our base is 10, and a set of symbols, including, and this is really important, a symbol for 0. Because when you don't have a symbol for 0, it's really hard to represent numbers. So the symbol for 0 is really, really important. And then 1 for each counting number less than the base. So for instance, in the system, the base 10 system, which we call the decimal system, the symbols that we use, or the digits that we use, are, and we go from 0. No, we don't really use a digit for 10. If you remember, if we write a number like, let's jot a number up here, 230, what the positional system tells us is that this 2 here tells us there's 2 times 100 in that number, and there's 3 times 10, and there's 0 times 1. So once we get up to 10, what happens in our numeration system here in place value is we go to the next position. So when we were counting up ones, when we got to the 10th one, instead of writing a 10 here, we write a 0 and we go to the next place in the number. And so therefore the numbers we're going to use, the digits, are going to be 0 through 9. And again, the position values in our system, in the US system, are 1. These are the ones. The 10s, the 10 squared, which is 100, 10 cubed, which would be 1,000, etc. So you notice they're being multiplied here by our power of 10 every time we go over to another position. And expanded form, this is to evaluate a numeral. In this system, we multiply the first digit on the right by 1, and then by 10, and then by 100, and so forth. And the reason that we do this is when we're going to change bases in a minute, we're going to need to understand the number in expanded form. So this number in expanded form is, if you start over here, 4 times 1, 3 times 10, or 10 to the first, 2 times 10 squared, or 100, and then 1 times 10 cubed. And again, we call this expanded form, and this will become very, very helpful, like I said, when we get into change of base in the next section. So let's look at some other, or there's the other representation. Let's look at some other positional value systems. The Babylonians used a system, and this was the oldest system that represented a place value. It was developed about 2500 BC. And it resembled a place value with a base of 60, which is called a sexagesimal system, base 60. And it was not a true place value because it didn't have a symbol for 0. Remember I said before, that's such an important concept of 0. This one doesn't have a symbol for 0. And so this leads to confusion because when they want to put a 0 in the number, they leave a blank. And so if you miss that blank, you're not going to interpret the number correctly. They only have 2 numerals that they use. They use this little dagger and then this little arrow. So this is the 1 and this is the 10, and that's all they need to write their numbers. And the positional values in the system are 1, 60, 60 squared, 60 cubed, etc. Okay, so instead of 10 and 10 squared and 10 cubed, we're going to go with a base of 60 in this system, in the Babylonian system. And a gap is left to distinguish between the place values. From right to left, the sum of the first group of numbers is multiplied by 1, just like we saw in our system, and then the next group is multiplied by 60 and by 60 squared and so forth. And this symbol, this is an important one to remember. This tells you you're going to subtract whatever follows it from the number before it. Okay, so let's take a look at this one. It says, write this, the Babylonian number, as a Hindu Arabic numeral. So here's the representation, and notice there's 2 groups here. So this is going to be the 60s, and this is going to be the ones, or the units. So how many do we have on the 60s? So we have, remember, this is 10, 10, 20, 30. So it looks like there's 34 there. And over here it looks like 10, 20, 21. So what we do is we're going to multiply, add them up. This is going to be 34 times 60 plus 21 times 1. And if you simplify that, you come up with 2061. So this representation here is the number 2061. All right, let's go the other way. So let's take a number in our Hindu Arabic system and translate it over to the Babylonian. Now what you do is you divide the number you're trying to write in the other system by the largest positional value less than or equal to the number. So if I skip back just for a second on the slide where I had the positional values, hold on a second. No, it wasn't there, hold on. It's on the prior slide. Yep, here it is. Okay, so here's the positional values in the Babylonian. 160, this is actually 360, and this is a big number. Let me just multiply real quickly. 60 cubed is, oh, that's not right. Helps to put the number in correctly. 216,000. Okay, so when we look at our number that we had, that's 7223, the biggest positional value less than or equal to it is going to be 360. I'm sorry, 3,600 rather, 3,600. So you're going to take 7223, divide by that number, and I get 2 with a remainder of 23. How do I find the remainder? 2 times 3,600 gives me 7,200. Subtract from 7,223, and I get a remainder of 23. And now I'm going to go to the next positional value, which is simply, so there's 2 groups of 360. The next position is 60, but 23 is less than 60, so there's not going to be any units in that second position, in the 60 positional value. And then I've got 23 in the units or the singles. So 2 times 60 squared, so 2 times 3,600 plus 0 plus 23 will get me back to my number. And then I'm going to translate that over to the symbol. So there's no 0, so what am I going to do? I'm going to leave a bigger space between this grouping and this grouping. And this is where confusion can come in this system, because if I don't leave a big enough space, people might misrepresent it or think that this equals is falling in this place here. Yeah, this is a problem with this system. This is why there were changes along the way, because it became very confusing. If you thought this fell here, the number was different then. So they leave a bigger space, and that's why it becomes important again that we have a 0 to represent, that we actually have a symbol for 0, which is where the other systems come along, which is where we go to. So that was a Babylonian. Now we go to the Mayan. Okay, and the Mayan were written vertically. Remember the Chinese ciphered system that we had last week was also written vertically. The unit positions are on the bottom, just like that Chinese system. We work up. The numeral in the bottom row is multiplied by 1. Now this system's really confusing. The next positional value is 20. And then the next positional value is 18 times 20, or 360. And then the next one is 18 times 20 squared, and so forth. So this one's a strange one because the base doesn't really stay the same for each of the positions. And then here are the symbols. Oh, here's the positional values. First of all, 1, 20, 360. This one's going to be 7,200, and so forth. There we go. And then here's the symbols that they use. So they have a 0, which is really, really helpful. And then if you notice here, they go 1, 2, 3, 4, and then they add a horizontal line rather, and they start again 5, 6, 7, 8, 9. There's actually a nice pattern to this. Then they have 2 vertical lines for 10, add the dots above, and then 3 vertical lines for 15. So there's a nice patterning to the way the symbols are put together. But importantly is that there's that 0, which is really, really, really helpful. Okay, so let's try a problem. Let's go from Mayan to the Hindu Arabic. So remember, we work from the bottom up. So we're going to start down here. And this is going to be 4 times, notice that's 4 times 1. And then we go up, we notice a 0. So here we have nothing in that next spot, 0 times 20. And then we go up here and we've got 8 times 18 times 20. And then we go up here and we have a 2, and remember the pattern, 2 times 18 times 20 squared. And then we add everything up. Oops, sorry, sometimes this website messes up my stuff. This should be over here. The number is 17,284. Okay, now we're going to go the other way. So now we're going to go from Hindu Arabic to Mayan. We're going to do the same thing. You're going to divide the number by the largest positional value less than or equal to 4025. If you remember, it went 360 and then it went 7200. So the smallest or the largest one that's less than the number is 360. So I divide 4025 by 360. I get 11 remainder of 65. So now my next positional value, there's 11 groups of 360. The next positional value is 20, which is less than 65. So I'm going to divide. And I get 3 with a remainder of 5, and then I'm into the digits. All right, so let's write the number. So there's 3 groups of 20 with 5 digits remaining. So what I've got here that's going to help me when I'm picking my symbols is, whoops, I've got 11 groups of 360, and then I've got 3 groups of 20, and then I've got 5 for the single digits. So again, there it is written out. So here's what I need. So I need 11 times 360 in that position. So that's the top position here. And 11 is right here. So the top one is going to be 11, and then the 3, and then a 5. So again, you start from the bottom up. 5 times 1, 3 times 20, 11 times 18 times 20, and so forth. Okay, questions on the 2 systems, Susan. We have the Babylonian, which has no true 0, and then we had the Mayan, which has a symbol for the 0. Babylonian was written horizontally, and this one's written vertically. This one has a true 0, a 0 symbol. Okay, good. All right. And by the way, when you're tested on this, obviously you'll be given these tables because there's no way you can remember all those symbols. Okay, yes. All right. So let's go on to the next section, which is other bases. So we kind of touched on this with what we just did, but sometimes we want to write numbers in other bases. And again, let's talk about the positional values in our system. If you remember what they were 1, 10, 100, 1,000, 10,000. Positional in the Babylonian were 1, 60, 60 squared, 60 cubed, 60 to the 4th, and so forth. So those are called, these 10 and the 60 in these are called the bases. And the reason for that is they determine the value of the position. So the base here is 10, 10, 10, notice 60. Okay, so we can have other bases. So any counting number greater than 1 can be used as a base. If a positional value system has a base b, like 10, then the positional values are going to be 1, the base squared, the base cubed, the base to the 4th, etc. So no matter what system I want to work in, I can determine the positional values in this pattern. So for instance, if I wanted to do a base 8, here's my positional values. 1, 8, 8 squared, which would be 64. 8 cubed, I don't know all these off the top of my head. 8 cubed is 512, etc. We could do base 2. So we'd have 1, 2, 2 squared, 2 cubed, 2 to the 4th. So a nice pattern. So what we can do, just a couple trivia things here. Base 6 occurs in combination with base 12, and it's called the duodecimal system. And our society, the U.S. society, has some remnants of this. We have 12 inches in a foot, 12 months in a year, 24-hour days. Gross, we talk about a gross of pencils, 12 times 12. 60, we have 60 in time. Angles, we have 60 seconds in a minute, 60 minutes to a degree in angles. And computers and other electronic devices use 3 different numeration systems. They use a base 2. People always talk about base 2. That only has the digits 0 and 1. It also uses, and then this is where we switch things on and off, with 0 is off and 1 is on. All computers can be converted to a series of single binary digits. And each binary digit is known as a bit. Octal is base 8. And groups of 8 bits of data are grouped to form a byte. And ASCII code, you may have heard of ASCII code. In ASCII code, this byte represents a capital A. And then notice what I want to do if I want to put a lowercase a, all I do is change this from 0 to 1. And that's in ASCII code. And you can look on the website, www.asciitable.com, to see all the representations. The other base that computer systems use is 16. And this is used to create computer languages like HTML, CSS, and both of those are used heavily in creating internet web pages. And computers can easily convert between the 2, the 8, and the 16. So now talking about the systems themselves, a place value system B has B distinct objects, 1 for 0 and 1 for each numeral less than the base. So remember in base 10, we said the digits that we were going to use were 0 through 9. So in base 6, we're going to use the digits 0 to 5. All the numerals in base 6 are constructed from those 6 symbols. Base 8 would go from 0 to 7, and again, all the numerals that we want to represent in base 8 can be constructed from those digits or symbols. So a numeral in a base other than 10 will have a subscript next to it to represent, to tell you what base it is. So 1, 2, 3, subscript 5 tells us this is the number in the base 5 system. 1, 2, 3, 6 is in base 6. These are not going to be the same number when we convert them to our base 10 system. So you want to make sure you understand that they're not the same. Base 10 usually are just written like this. We don't usually put a 10 below it because it's implied that this is in our base 10 system. And again, symbols that represent the base itself in any base are written like this: 1, 0, base B. So in other words, in base 5, this 10 represents 5. And if we do the expanded form, you can prove that. So this is 1 times 5 plus 0 times 1 equals 5. To change a numeral from one base to another, multiply each digit by its respective positional value and then find the sum, this is going to base 10, of those products. So let's try an example. We want to convert 312 base 4 to base 10. So again, what I'm going to do is I'm going to write it in expanded form in the base 4 system. So I take 3 times, remember the positional values now for this are going to be 1, 4, 4 squared. So 3 times 4 squared plus 1 times 4 plus 2 times 1. And now I go ahead and I multiply out and add them together. So 3 times 16 plus 1 times 4 plus 2 times 1. And I get 48 plus 4 plus 2. So this is equivalent to 54 in the base 10 system. So this is how we represent the number 54 in the base 4 system. When I take this and I convert it back to base 10, I come up with 54. Okay, let me see. Oh, and just something to observe too. If you have a number that's less than the base, so in other words, 2 base 4 has the same value as 2 base 10 because they're both equal to the number 2. So if n is a digit less than the base, then the base is less than or equal to 10, then n base b equals n base 10. So as long as the number you're representing here is less than the base, if we're talking about base 10 or less, then the number is going to be the same. So just a little bit of trivia. Okay, let's go do another one. We want to take a base 2 number and convert it to base 10. So again, you're going to write it, expand it. Remember the positional values here: 1, 2, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, etc. So 1 times 2 to the 5th plus 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 0 times 2 squared plus 1 times 2 plus 0 times 1. And then we go ahead and simplify. So this is 1 times 32 plus 1 times 16 plus 0 times 8, 0 times 4 plus 1 times 2 plus 0 times 1. And so what do we end up with? 32 plus 16 plus 2, which is equal to 50. So this number, this representation of a number in base 2 is equal to 50 in base 10. Okay, so this was all converting from another base to base 10. Let's go the other way. So we want to convert now the base 10 number to a different base. So just like we did in the last section when we were working with the Mayans and the Babylonians, we're going to divide by the highest power, the highest positional value in the new system that's less than or equal to the number that we're dealing with. And we're going to keep doing this. So let me give you an example. It's easier to look at an example. Let's convert 273 to base 3. Okay, so what I need to think about is, what are the positional values in base 3? So what are they going to be? I'm going to start with a 1, and then I'm going to go 3, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, 3 to the 6th. And then if I multiply those out, what do I get? 729 is 3 to the 6th. 3 to the 5th is 243, etc. And what I want to do is find the largest positional value less than or equal to the number I'm trying to convert. Okay, so the largest one here is going to be this 243. Okay, so I'm going to start out dividing the number 273 by 243 and then work downward. All right, so here's a little pictorial from your book. So 273 divided by 243 gives me 1 with a remainder of 30. So then I move to the next positional value, which is 81. 30 is not less than 81, so I can't divide by 81. So I'm going to just skip this spot and put a 0 there. I'm going to drop to the next position. 30, the next positional value is 27. 30 divided by 27 is 1 with a remainder of 3. I'm going to drop this 3 down to the next position. 3 is not greater than 9, so I'm going to put a 0 in that position, and then 3 is going to end up in the last position here. This position is valued 3. 3 divided by 3 is 1 with a remainder of 0. So here's the representation right here. So it's going to be 1, 0, 1, 0, 1, 0, subscript 3. So we don't forget that we're converting to base 3. So again, if you do this in expanded form, check it out. Here we go. Here's what we just did. 1 times 243 plus 0 times 81 plus 1 times 27. Remember the pattern. It was 1, 0, 1, 0, 1, 0. And so I end up with 1, 0, 1, 0, 1, 0, 3. Okay, I kind of like this way back here. Let me just get back to the prior screen because it lays it out really nicely for you as you drop down, and then your number, your new representation of the number is going to be right here. So depending on which way is more comfortable for you, I kind of like that other way. So it's 1, 0, 1, 0, 1, 0, 3. And then again, you could expand it and make sure you get back to 273 as a check. Okay. Are you still with me, Susan? Are you okay? Okay, good. All right, so the last thing to cover in this section is what happens when we want to work with a base greater than 10. Remember we said with computers they work with base 16. So we need some single-digit symbols to represent numbers greater than 10 or 10 or greater, like 10, 11, 12, etc., up to 1 less than the base. So up to 16 we would need 5 more symbols, right? We need a symbol for 11, 12, 13, 14, and 15. And so what we do in this book, and this is not all mathematicians do it this way, but we're going to use a capital letter. So we're going to go A, B, C, etc. for as many symbols as we need. So for instance, in base 12, we're going to use the symbol 0 up to 9. And then we need 10 and 11, so we're going to use a capital A and a capital B. And remember, once we get to 12, we go to the next position value. So if we use base 16 that we mentioned before, the hexadecimal one, we're going to go 0 to 9. And then again, we're going to have to add on to this. So we've got 10, 11, 12, 13, 14, and 15. So those are going to be our symbols. So let's try an example. We're going to do 1 from base 16 to base 10, and then we're going to go from base 10 to base 16. So let's try this one. So we're now in base 16 and we want to convert this number to base 10. So what we're going to do is we're going to write out the expanded form. Remember the positional values here are 1, 16, and 16 squared. So we've got 7 times 16 squared plus D times 16 plus E times 1. So you're just going to have to jot on the side, remember what D and E are equal to. And we had that on the prior screen. So D is going to be equal to 13 and E is going to be equal to 14. So 7 times 256 plus 13 times 16 plus 14 times 1. And then we just multiply and add them together. So this representation of a number in base 16 is equal to 2014 in base 10. All right, let's go the other way. Let's go from base 10 to base 16. Now again, you want to think about what's the highest positional value less than or equal to this number. So this numbers again were 250, it went 1, 16, 256, and then we get to 4096, and that's going to be the greatest positional value, 16 cubed, less than or equal to 6713. And again, here, when we're dividing, if we get a quotient greater than 9 but less than 16, we're going to use those letters A through F, like we just did in the prior problem. So again, a little picture from your book. So 6713 divided by 4096, it goes in one time with the remainder of 2617. We're going to drop to the next position, which has got a value of 256. So take 2617 and divide by 256. And when you do that, lo and behold, when you actually divide it, you come up with a 10, which is represented by an A now, with the remainder of 57. Drop the 57 down to the next position, which is a value of 16. 57 divided by 16 gives me 3 with a remainder of 9. So here's my representation here. 1A, 3, 9, base 16. 1A, 3, 9 in base 16. And again, once you've converted it, you can expand it, put it in expanded form and check and make sure that you did it correctly when you go back to the other base, or back to base 10 in this case, sorry. Okay, questions? I think that's the end of the problems that I had to go over. Yeah, that's the last one. So we went over the positional values and then we went over the change of bases. Okay, good. Now next week, I think we only do one section next week. We're going to jump over to section, let me just pull out my little weekly schedule here, section 5.8, which is the Fibonacci sequence and the golden ratio. So one section for next week. And we're still in Unit 1, just to remind you of that. So we only do the first 4 sections in Chapter 4 on the bases and the numeration systems. Okay, good. All right, Susan, have a great week. And again, we'll chat again next week, and we're skipping up to section 5.8. All right, take care.